viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryabhat College, University of Delhi. As you all are aware that presently we are working on a series of algorithm analysis and designs. Within this series we are presently going through the topic of dynamic table under the umbrella of amortized analysis, and in this topic of dynamic tables or in amortized analysis we have covered all three strategies of amortized analysis, and now we are on to looking into how we are going to incorporate or how we are going to use those strategies while analyzing the operations on dynamic tables. So with this background, let me begin with today's lecture with a quick introduction or a quick recap, I can say. So here the dynamic table can be a dynamic array that is going to shrink or that is going to grow on the basis of the application or on the basis of context, and looking at what operations we are going to analyze this particular data structure. So the operations here will be insertion operation and deletion operation, and as you all are aware that insertion and deletion are most common operations, and amortized analysis is performed because when we are looking onto a sequence of operations, some of them which could be costly. So here a dynamic table is a data structure on which many insertion and deletions are performed frequently, we can say. So amortized analysis sets is its base for the analysis, and in because a sequence of insertion and deletion operation will be performed here in some order. So we will be going with amortized analysis. So now let us consider a quick kind of how this table grows or how this table shrinks. So let us consider the figure which is available on the screen. As you can see, initially I am having kind of, we can say, no data structure with no memory. Then we have allocated one space or one cell for that data structure, for that table or for that array, we can say. And when we want to insert another item which is 12, we want to expand the table because there was only one space. Then the table was expanded at the second step, then at the third step again table was expanded, fourth step there was no need, and fifth step again the table was expanded. So in this manner this expansion of table happens here, and this is what we have already covered up to a greater length of detail. Taking a flashback of terminology, here we are analyzing the operations using potential method. So potential method, the moment I say potential method, we need to coin a potential function. So potential function with which we are working till this point is twice into num of t minus size of t, where num of t is number of elements in the table T, while size t is the size of the table T. And initially when there is no element in the T, or even that in the table, or even that table T is not existing, we can say num of t is equals to 0, and so is size of t is also equals to 0. So therefore phi of t is also 0. So this was kind of a set base for the terminology which we will be using in today's lecture. And when we can say number of elements in the table T, which is num t, is equals to size of t, then phi of t by the formula twice num t minus size t will be equals to num t. And if num t is equals to size t by 2, my phi of t is equals to 0. So here we have another very important term on which today's whole analysis is going to be based, and that term is nothing but alpha, which signifies the load factor. So load factor here is we can say a measure of how much percentage the table is filled. So that alpha is defined or calculated by num t divided by size of t. So, our today's analysis will be based, will revolve around this alpha factor with this load factor alpha. Now, coming to when we need to grow the table or when we need to shrink the table. So, here whenever let us say we are performing some insertions and we do not have the space, we need to expand the table, and when there and when we have a kind of calculation or have a scenario when my table is underutilized. So, table is underutilized in a sense means that table is not having enough number of elements to be stored as compared to its size. So, we need to shrink the table because memory is in a way we can say unused. So, we need to coin different strategies, or we can say very sensible or reasonable strategies for growing and shrinking the table, because what actually we are looking for, that these application does not go for expansion or contraction frequently. Now, why we are focusing on non-frequent expansions and contractions? Because the expansion and contraction both are here very costly operations, because in this what are we doing in both the processes? What are we doing? We are just taking elements from one table and then we will giving it to storing the elements into another table, and then the whole table will be transformed from new to old, we can say. So, it is a kind of very costly process in terms of computation. So, the idea is that my application should not go for expansion or contraction very frequently. That means, we need to coin the strategies for growing the table or for shrinking the table in a manner that these expansion and contraction should be, we can say, not very frequent. So, this is what we are looking for, and with this background we have already seen sequence of n insert, for which the amortized cost for the whole n insertions, the amortized cost for the whole sequence of insertions is has come up with n into order of 1, which is order of n. So, order of 1 amortized cost for one insert, and if we are having n inserts in the sequence which we are performing, then we will be having n into order 1, which is order n. And we have seen both the cases here. Both the cases means there could be one case in which your table is expanding while inserting, or there is a requirement of expansion because there is no element to be inserted. That is one case. Another idea could be the space is already there and you just need to insert the element. So, whether you want to, whether the table is going to be expanded, yes or no, for both the cases we have already seen the insertion analysis in the dynamic table, which is obviously based on the amortized technique, and the amortized cost for n inserts is coming up to order n. This we have already seen. Now, let us try to understand this expansion and obviously contraction, coming up the contraction to coming up onto the contraction to when the table is expanding, I can say the potential associated with the table is going to be 0, and when the table is full, the potential is number of elements in the T. Now, please try to connect the dots that what actually is happening here. When the table expands, the potential associated is 0. That means whatever potential has been accumulated before expansion has been we can say used for expanding or for moving the elements from the new to the old one. And when the table is full, we have enough potential, and that potential is equals to the number of elements into the table, and whenever the next element is going to be inserted there, this potential which is equals to num t is going to take those elements as, or we can say is going to pay for insertion of elements or moving of elements from the original table to the new table, because an expansion is occurring. Now, these are two extreme cases, when the table has just finished its expansion and when the table is full. So, what about all other configurations? So, if we can see in all other configuration, the potential will always lie between 0 and num t. So, either the potential is going to be greater than 0 or it is going to be less than num of t. By the formula, by my potential is twice num of t minus size t. So, with this formula we can calculate potential for any scenario of this dynamic table, and potential for all other configurations except the table is full, or except when the table has just expanded. Except these two extreme scenario, for all other configurations my phi of t is going to be going to lie between 0 and num of t. So, obviously we can say my phi of t is greater than equals to 0 always, which is we can say kind of constraint, or which is one thing which we need to make sure that the potential is always greater than equals to 0. It should not be, it must not be in negative terms. So, this is what we have ensured by taking my potential function as the calculation of twice of num t minus size t. Now, let us see, we have already covered we can say insertion. Now, coming up to, let us say we want to analyze something about deletion, or we want to analyze the or we want to see the amortized cost for the operation of deletion. So, just to recall, the amortized cost is equals to the actual cost plus potential difference, where the potential difference will be given by the potential after the ith operation minus the potential before the ith operation, which are denoted by phi of I minus phi of I minus 1 respectively, I can say. So, here now the actual cost for deletion is obviously I mean we are aware of it, that actual cost for deletion is 1. So, we have put in 1 here. Now, phi of I by the set formula of potential function, it is going to be 2 into n of I minus s of I, where n of I and s of I are number of elements and the size of the table after ith operations. Then it is going to subtract the term in the bracket which is at the second step of this derivation, which is shown on the screen, that is 2 num of I minus 1 minus s of I minus 1. So, basically what we have put in up with the formula, we have put in up the amortized the potential function before the ith operation, that is going to be subtracted from the potential after the ith operation, and this is going to give me what? This is going to give me the potential difference. So, yes, here we are set with this second step. Now, coming to the third step, as we can see that here there is no change in size, at least. That means size after ith operation and size before ith operation are same. That means s of I is equals to s of I minus 1. That is one thing which is set here, but this is not related, or means this does not go with your num of I. So, num of I, which is denoted by n of I here, because we are deleting one element from the table, the number of elements after ith operation is obviously going to be 1 less than the number of elements before ith operation. So, we can say s of I is equals to s of I minus 1, while num of I is equals to num of I minus 1 minus 1. So, that means we are decreasing one element from the previous table. So, putting these values into the expression we are going to get. So, here at the third step of this derivation, we have put in up n of I minus 1 in place of n I, and S of I minus 1 has been replaced by S of I, as they both are, we can say, in a way equal. So now the expression has become 1 plus 2 into n of I minus 1 minus 1 minus S I as taken from the previous step minus 2 n I minus 1 minus S I, and here we have replaced S I minus 1 with S I, as they both are equal. And after performing some simple calculation, we can see that n of I minus 1 is a term which is going to get cancelled. Then we have minus 2 and plus 1 the constants, while SI's terms of SI's are going to be cancelled. So minus 2 and plus 1 will remain as constants. So that is going to give me the final situation as minus 1. So I can say what? I can say amortized cost for deletion in the dynamic table is going to be minus 1, and minus 1 is, we can say, yes, it is a constant. So thus we can establish the result that amortized cost of deletion is minus 1, which is order 1, we can say constant. Yeah, we are fine, we are okay with this point. But let us look at our own strategy which we have coined. What is actually happening? When are we expanding the table? When are we contracting the table? Now see what is happening. Expansion, as you all are aware, is happening when a new insert is there and we don't have the space to take up that element or to insert that element. So that means we are expanding when the table is full, and for this expansion, what are we going to do? We are going to create a new table whose size is twice the size of the old table, and then we will copy all the elements from the old table into the new table, and obviously then we will be inserting that element which we need to insert, for which we have triggered the insertion operation. So in this way insertion happen, and so as the strategy for expansion is this. That means when the table is full, we are going to expand the table. Fine. What about contraction? So if we look at the contraction, the first strategy that comes up to mind says, when are we expanding? We are expanding when my table is full. So obviously we will be contracting when my table is half full. So when my table is half full and ith operation is delete, that means now the table number of elements in the table will go by less than 50% or less than 1 by 2. So my table size is going to below, my table size go below size by 2, then we are going to perform contraction. That means number of elements are we can say less than half of the size, then we are going to perform contraction. So now we have two set strategies for contraction as well as for expansion also. For both for each of the scenarios we have strategies. Fine. Now let us consider an example with some sequence of operations on this table. So sequence of operations says what actually is happening. Earlier operation says insertion, 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 and some insertions, and then we have one more insertion. I am just going to explain. One more insertion, then 2 deletions, and then 2 insertions, then 2 deletions, followed by 2 insertions, and so on and so forth. So looking at this sequence of operations, what I want to establish here is, first of all, the insertions in the starting of this sequence are n by 2 inserts. So initially my table is going for n by 2 insertion operations, and rest of the operations which are shown in the different color are rest n by 2 operations. So first n by 2 operations are just insert only, and the rest n by 2 operations are insertion followed by 2 deletions and 2 insertion and 2 deletions alternatively. So this is what is happening here. Now see, we can say here, looking at the sequence, that first n by 2 insert operations, then n by 2 plus 1th operation, that means next to half of the operations is insert, yes, and with this insert the table is going to contain size by 2 plus 1 elements, that means half of the elements equals to half of the size plus 1, because we are going to insert one more element. So, now table has been, we can say doubled, expanded, and then got on to the double, fine. Now, in the sequence we have, if you can see, 2 deletions. So, 2 deletions are going to bring down the number of elements in the table to size by 2 minus 1. So, earlier we have size by 2 plus 1 elements after the insertion, then one deletion is performed, it is going to be size by 2, then one more deletion is performed, it is going to be size by 2 minus 1. So, the moment we have number of elements present in the table as size by 2 minus 1, this is going to trigger a contraction. Now, please remember, we have just expanded the table before the ith n by 2 plus 1th operation, and then just after 3 operations we are contracting it. Now, again let us say we perform 2 insertion operations, this is going to be again kind of, we can say, insertion operation triggers expansion, and then again further 2 deletions is going to give you a contraction. So, looking at the sequence, we can say we have an kind of half full table for the first n by 2 inserts. Till first n by 2 insert we have a half full table, then we have one insertion, number of elements will become size by 2 plus 1, fine, one deletion, elements size by 2, one again deletion, element size by 2 minus 1, then we are going to contract it. So, contract, size reduces, then we perform 2 more insertions, then these 2 insertions are going to trigger an expansion. So, basically what I am trying to say? I am trying to say that what actually is happening in the above example, we can see that expansion and contractions are happening alternatively for every n by 4 times. So, every we can say 4 operations, 2 insertions, 2 deletions, you perform expansion and contractions, again 2 insertion and 2 deletions, after a certain point of time, again you have kind of, we can say again expansion and contraction. So, now looking at this strategy, is it a good strategy? So, please try and understand that it is triggering expansion and contractions too frequently, which is not the idea. And if we come to the cost analysis of this sequence, this is going to be kind of very costly sequence, because first n by 2 operations are just insert operations, as I told you. So, amortized cost of insert is 3 for n operations. So, 3 into n is going to give me an order n term, while those second n by 2 operations are incurring cost of order n, because it is giving you we can say expansion and contractions alternatively every n by 4 times. So, what is happening here? The cost of sequence of n by 2, the next half n by 2 operations is going to be order n square, and this is going to blow up the whole term. The total cost of n operation is going to be order n square when you are going to sum up the order n term for the first n by 2 operations and order n square term for the next n by 2 operations. The whole sequence of n operations is going to be as costly as order n square. So, this a frequent contraction and expansion has blowed up the whole term. This is what the problem with this kind of strategy is. That means we need to change the strategy of contraction and expansions. We need to relook upon this strategy of contraction and expansion. So, this is what the problem with the established approach, when we are saying that my potential function is twice into num of t minus size of t. This is going to give us problem at some point of time. So, hope you have enjoyed the lecture. In this today's lecture, we have seen what is the problem with the current strategy, and this problem will be resolved in upcoming lectures. Thank you for the patient hearing.